Hi everyone, today we're going to be talking about topic 4.5, stoichiometry. Now a lot of this will serve as review, as we've already talked about stoichiometry previously in Honors Chem, and we've been using stoichiometry so far throughout the year, but it is important to always keep stoichiometry in mind, especially as we're going to look into more reactions and thinking about what happens during reactions, before reactions, and after reactions. And so stoichiometry is the relationship between relative quantities of compounds in a chemical reaction. So, as for example, let's say I have the reaction of methane, which is CH4 gas, and oxygen, O2 gas. This would do a combustion. This would make carbon dioxide, or CO2, again as a gas, as well as water, or H2O as a gas. Now, of course, this just tells us what we have at the start of the reaction, what we have at the end of the reaction, but we always must remember the law of conservation of mass. And so we have to have the same amount of everything at the start as the end. And so we should have 2 oxygens and 2 water molecules. So we have the same amount of carbon, oxygen, and hydrogen on each side. Now, the reason that we care about stoichiometry is because there's a lot of different values and parameters that we can determine using stoichiometry. Firstly, we've done this quite a bit already. We can determine the number of moles or grams of a compound made in a theoretical reaction. So if I give you some sort of a chemical equation, I should be able to calculate the number of moles of grams of something that I'm making given a starting material. I can calculate the number of moles or grams of a compound made in an actual laboratory reaction. So if I have some actual parameters that I measured inside of a laboratory, I can calculate how much moles or grams of compound I actually made based on what I expect to get. I can calculate what's known as the limiting reagent or reactant in a chemical reaction. And this is basically what stops the reaction from continuing. I can calculate the excess reagent or reactant in a reaction. And this is the compound that is left over once a reaction is done, or what's in excess. If I have too much of something, I should have that left over at the end, and I can determine which one of my reactants that is and how much of that is in there. And then finally, I can calculate what's known as the theoretical yield and the percent yield, where the theoretical is how much, not what, but how much I expect to make, and the percent yield is the percentage that I actually made. We've already had a little bit of experience with this in our first lab. Now, if we're interested in calculating the limiting reagent or the limiting reactant of a reaction, there are a few steps that we need to take. The first step, number one, what we want to do is balance the chemical equation. This should really be the first step anytime you get a chemical equation, is just check if it's balanced. If it's not, go ahead and balance it, because you really can't get any information out with an unbalanced equation. The second step is to convert to moles. And so if you have grams, then you convert to moles, right, using the molar mass. And if you have molarity, you calculate the moles as well, and that's using the volume. Step 3 is you multiply by the mole ratio of the compounds on the reactant side. And there's 3 scenarios that we'll get right here. Scenario A is essentially if each compound or compound is reacted all the way, the calculation tells you how much you would need to run the component out. In other words, it tells you how much is required for the reaction to actually fully occur. That's scenario A. Scenario B is that if we do not have enough to react completely, then that is the limiting reactant. So if you multiply by the mole ratio and you don't actually have enough for the reaction to complete, that is the limiting reaction. If we do have enough to react completely, then that would be the excess reactant. Let's take this simple example first. And so student reacts 1 mole of HCl with 3 moles of NaOH, given this reaction here. And it's asking us what is the limiting reagent and what is the excess reagent. And so on our left side, if we want to balance this equation, we see we have 2 hydrogens, 1 from HCl, 1 from NaOH. We have 1 oxygen, we have 1 chloride, and we have 1 sodium. On the right side, we again have 2 hydrogens from H2O. We have 1 oxygen from H2O. We have 1 chloride from NaCl, and we have 1 sodium from NaCl. So this is already balanced. And so all we need to do is find the number of moles of HCl and NaOH, which are given to us here. And so if we want to do HCl first, we would take the number of moles, which is 1 mole, multiply it by the mole ratio. Since these are 1 to 1, the mole ratio is 1/1, and so we need 1 mole of HCl for the reaction. We do the same thing for NaOH. We have 3 moles of NaOH for the reaction. The mole ratio is 1/1, and so for the reaction, we have 3 moles of NaOH. because we only require 1 mole based on this mole ratio, we should have the one that has less moles after this calculation should be limiting. And so HCl is limiting and NaOH is excess. And if we want to determine the amount of excess NaOH, we just take the number of moles of NaOH, 3, and subtract the number of moles of the limiting reagent, HCl, minus 1. So we have 2 moles of NaOH remaining. Oxygen. Now let's look at a slightly more challenging problem. So here we have iron, or Fe, solid, and oxygen reacting to produce iron 3 oxide, Fe2O3. It's asking if we react 15 grams of iron with 6.5 liters of oxygen at standard temperature and pressure, how many grams of rust would form? It's telling us that there are 22.4 liters of gas per mole at standard temperature and pressure. So the first thing we want to do is write our balanced equation. And so we should have solid iron plus O2 gas reacting to make Fe2O3. I have 1 iron on this side. I have 2 oxygens on this side. On the right, I have 2 irons, and I have 3 oxygens. And so in order to balance out the irons first, what I could do is I could add a 2 right up here out front. And so now I should have 2 irons and again 2 oxygens. So my irons seem to check out here. But now I have 3 oxygens. That doesn't really, isn't very helpful. And so I could multiply this by 3 over 2 O2. That would get me 3 oxygens on this side, and I would have 3 oxygens on that side. But I don't really like having these fractions in here, and so I could just multiply everything by 2. And so what this would end up being is 4 Fe solid plus 3 O2 gas makes 2 Fe2O3. And so now if I do the calculations, I should have 4 irons and 6 oxygens on this side. And on this side, I should have 4 irons and 6 oxygens on that side. Anytime we have these weird, fractions here, you can always just multiply everything by the same number in order to balance the equation a little bit faster instead of, multiplying the left side, then going over to the right side. And so now I have my balanced equation right here. And so for every 4 moles of iron, I need 3 moles of O2. Or if I'm going to calculate a mole fraction, it would be 3 over 4. So now I have my mole ratio. Now what I need to do is calculate the number of moles of my reactants. And so for iron, I'm given 15 grams of Fe. I can divide that by the molar mass, which is 55.85 grams of Fe per 1 mole of Fe. If I do that math, I'll get 0.27 moles of Fe. Now for O2, I'm told that I have 6.5 liters of O2. I'm also told that 22.4 liters of gas is 1 mole at standard temperature and pressure, which I'm currently at. And so 22.4 liters over moles, that should give me the number of moles of O2. And if I do that math out, I get 0.29 moles of O2. Now I can multiply each of them by the mole ratio. And so for every 4 moles of Fe, I have 3 moles of oxygen. And for every 3 moles of oxygen, I have 4 moles of Fe. If I do that calculation, I get 0.36 moles for Fe, and I get 0.39 moles for O2. So now we compare right here. This one up here is lower. This is higher. And so my limiting reactant is Fe because I have less moles. And so now, if I want to determine how many grams of rust would form, right, because that's what my question's actually asking me, I would use this number of moles because that is the maximum I can actually make based off of this reaction. And so if I look at my mole ratio here, for every 4 moles Fe, I have 2 moles Fe2O3. And so I'd take the number of moles of Fe, 0.27 moles Fe. Again, for every 4 mole Fe, I have 2 mole Fe2O3. So I should divide this number by 2. And I'll get 0.135 mole. Again, I know the sig figs aren't right, but I'll round at the end. And then I take 0.135 mole and just multiply it by the molar mass of iron oxide, which is 159.69 grams per mole. And I get 21.56 grams, or, of course, because we're rounding, we have 22 grams of Fe2O3 at the end. Now, lastly, I just want to talk about percent yield. As a reminder, theoretical yield is the amount of compound you expect to make in a reaction. So for example, if I have the previous example, HCl plus NaOH makes NaCl plus H2O, if I have 2 mole of HCl, because it's a 1-to-1 ratio here, I expect to make 2 moles of NaCl. Now, of course, in a lab, that doesn't always happen, right? Sometimes you might actually end up making a lot less than you expect. And so the percent yield is the actual yield that you get in the laboratory divided by the theoretical yield times 100%. And these can either be in moles or grams, typically. And so in my example, let's say I expect 2 moles of NaCl. Let's say I actually only get 1.89 moles of NaCl. If I want to calculate my percent yield, I would take 1.89 moles NaCl. I expect 2 moles NaCl, and I would multiply that by 100%. And what I get is about 95% yield. We'll have a little bit more practice with this as well as limiting reagents in class, but otherwise, thanks guys.